Okay, so picking up where we left off, if you want to convert from scientific notation to the decimal form of a number, then you can basically take the decimal point and move it the number of spaces indicated by the exponent. And the way you can tell which way to move it is that if the exponent is positive, then you have to move the decimal point in the direction that makes the number bigger, because big numbers have positive exponents. If the exponent is negative, then you want to move the decimal in the direction that makes the number smaller. Okay, so if we look at an example or two, say 4.85 times 10 to the fourth power. In decimal form, you're going to want to take the decimal point and move it 4 spaces. The exponent here is positive 4, so you're going to move the decimal point 4 spaces in the direction that makes the number bigger, which is to the right. Because if you move it 1 space, you get 48.5. Move it 2 spaces, you get 485. Move 3 spaces, you get, well, that's interesting because the third and fourth space, there's nothing there. So move it 1 space, 2 spaces, 3 spaces, 4 spaces. This is where the decimal point ends up, and there's a gap there. So what you do is you just fill in the gap with zeros. And your number ends up being 48,500. One actually a fairly important thing to remember is, though, that if the zeros are not there in the original number, then don't actually write the decimal point in. If you write the number like this, it's understood that the decimal point is at the end, but don't actually write it in, because that will make a difference for the accuracy with which you're implying we know that number. And that will play a role in significant figures and error analysis, which we're coming up on soon. So 48,500 would be the number there. You can actually consider this to be sort of a reverse of the step-by-step process we did up above in going from decimal to scientific notation, because essentially what you're trying to do is get the exponent to be 0. So for a step-by-step approach, essentially what you want to do get the exponent to be 0. And you can do that by taking the original number and saying, okay, it's 10 to the fourth. If you want to do it step by step, our next step would be, what do I have to do to get this number to be something times 10 to the third? Well, what you'd have to do, since the exponent's getting smaller, you'd have to move the decimal point 1 space in the direction that makes the number bigger. Okay, so 48.5 times 10 to the third is the same thing as 4.85 times 10 to the fourth. 48.5 times 10 to the third, though, is not proper scientific notation, because the first part of the number is not between 1 and 10. But it does have the same value as what we started out with. Okay, the next step is you want to get the exponent to go down to 2. Well, to do that, all you have to do is move the decimal point 1 more space in the direction that makes the first part of the number bigger. So 485 times 10 to the second is the same thing as 48.5 times 10 to the third, and it's the same thing as 4.85 times 10 to the fourth. All of these numbers have the same value, but only the first one is proper scientific notation. Okay, if we move it 1 more, if we want to get the exponent, that is to be 10 to the first power, going down, taking the exponent down 1 step, then we have to move the decimal point 1 space in the direction that makes the number bigger. And that's our first space where there's nothing there. So you put a 0 in, but remember, don't write the decimal point if the zeros were not there to begin with. So 4,850 times 10 to the first power is the same as all of these other numbers. And then 1 more if we want the exponent to be 0, we move the decimal point one more place in the direction that makes the number bigger, 48,500. Again, no decimal point because the zeros were not there originally. And so 48,500 times 10 to the 0 has the same value as all of these other numbers. And because 10 to the 0 is 1, we can just drop that. And here you've got your decimal form of the number. And there was your original scientific notation form. Normally, when I ask for a numerical answer on a test or a quiz, I will be looking either for proper scientific notation or the proper decimal form. These intermediate forms here would not be acceptable. I mean, you get partial credit, but if you want full credit, it's going to need to be either the decimal form or scientific or proper scientific notation. As for which one to use, decimal or scientific notation, that's generally up to you unless I tell you that I want the answer in one form or the other. Generally, though, if the number is of a reasonable value, say on the low end, say a decimal point with maybe no more than 3 zeros and then a number, and on the high end, maybe in the hundreds of thousands or so, you can use a decimal form. If it's outside of that range and you'd end up writing a lot of zeros, that kind of thing, then you'd probably want to use scientific notation. And okay, one other example. A negative exponent. Well, in this case, that's going to be 6.83. Since the exponent's negative, you need to move it 3 spaces in the direction that makes the number smaller. So there's 1, and there's 2, and there's 3. When you're moving the decimal point backwards like this, you actually do, you write in zeros for anything, for any spaces where there's nothing, like we moved 2 spaces beyond the numbers that were actually written. So those are zeros, but you do write in the decimal point. So when you add zeros at the end of a number, you don't write the decimal point in, but if you add zeros at the beginning of a number, you do write the decimal point in. So this would end up being 0.00683. You can write the 0 before the decimal point if you want to. I usually leave it out because it's easier, unless I'm typing like for a test or a quiz, and then I'll put it in. You can put it in or leave it out as long as you're clear about where the decimal point is. And that should just about do it for our introduction to scientific notation. Be sure to look over Appendix B to make sure that you have a good understanding of the concept. And if there are any questions, you could always ask me in class or via email. All right, now we come to, since we're working on measurement, our next thing, we did the numbers up here, number. Now we have to talk about units. The units are agreed upon standard quantities that we use to compare the magnitude of what we've got to those standard quantities. And we use standard agreed upon quantities like inches or feet or centimeters or meters because everybody knows what they are. And so we can say this object has a mass of 2 kilograms. Well, basically everybody knows what 2 kilograms means. And so other people know what the mass is. And there are conversion factors that you can use. If you don't know what a kilogram is, you can look up the conversion factor and convert kilograms to pounds, for instance, and then maybe you'll know what it is. Okay, so we compare it to known defined units. This is also something that I liked the way the old book did it, so I'm going to go back and refer to my old notes. The units of measurement that we use in science we use the metric system, of course. The metric system is much more sensible than the English system because, for one thing, in the metric system, everything is based on factors of 10. So you can very easily do many conversions within the metric system simply by moving the decimal point around in the number without actually even having to bring out your calculator. In the English system, you have a lot of very eccentric relationships between quantities, like 12 inches in a foot and 3 feet in a yard and 5,280 feet in a mile. And where did they come up with this stuff? 16 ounces in a gallon. Where did that come from? Or sorry, is it 16? 16 ounces in a pound, and using the same unit, ounces, for both weight and volume. That's kind of weird too. So the English system has just got a lot of stuff wrong with it. The metric system, like I said, it's all based on tens, so conversions can be very useful. We use in chemistry and physics what's known as the SI system, or Système International. Which is French, but anyway, it's the international system, which is a subset of the metric system, which means that certain types of units or certain types of measurement will have a standard unit that's used for them, which makes calculations easier. There are lots of equations where if you do a measurement in the standard SI unit and put that number into an equation, you will get out another SI unit. Whereas if you just use some other unit, you'd end up with some weird quantity that wouldn't really be easy to compare to anything else. And so there are standard units in the SI system for each type of measurement. For length, and of course, any kind of linear distance. So not only length, but width, height, depth, and distance for that matter. The standard unit would be the meter. The abbreviation in the metric system for meter is M, lowercase m. And just for comparison, a meter is 39.37 inches. So it's about 3 1/3 inches longer than a yard. So in general, you can, at least to an approximation, think of yards when you think of meters. There are certain units that are derived from length or distance. One of those would be area. So if you're dealing with a two-dimensional surface like a land area, or say the area of the cover of a book or something, that is basically length times width. And those are both distance measurements. So the official SI unit for both of those would be meters. Units act like numbers when you multiply and divide. So if you multiply a number in meters by another number in meters, the unit ends up being square meters, or meters to the second power. Okay, so that would be the official SI unit for area. You know, if I ask you the metric unit for volume, you'd probably say liters, duh, or maybe milliliters. But in the SI system, volume is considered to be length times width times height. And those are all distance measurements, so they're all officially measured in meters. So the official SI unit for volume is cubic meters, or meters to the third power. For mass, the standard unit is probably what you would guess in the metric system, kilogram. For which the abbreviation is kg, lowercase g for grams, lowercase k for kilo, which means 1,000. So as we'll see in a minute when we get to the metric prefixes, kilogram means 1,000 grams. It's the only one of the SI units that actually has a prefix already attached to it. Okay, and that is approximately 2.2 pounds a kilogram. Or a pound is about half a kilogram. Time, the standard SI unit for time is measured in seconds. And don't worry, this is not some kind of weird decimalized metric second. They actually haven't managed to decimalize time and have it work out. Although during the French, actually the metric system was devised during the French Revolution, where they tried to bring hyper rationality to every aspect of life. And with most measurements, like length and width and height and mass and volume, it worked just fine. But they also tried to decimalize time, and that didn't work out so well. So they eventually gave up on that and went back to these standard 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So this seconds here is the same second that we use in the English system. But because seconds is considered to be a metric unit, you can use standard metric prefixes with the word seconds. So like if something happens over a very short duration, you can have milliseconds, just like you can have a millimeter. A millimeter is 1/1000th of a meter, and that's the tiny little divisions on a metric ruler. Well, a millisecond is 1,000th of a second. For longer times, you can use, hours or minutes, hours, days. But if you want to use the time in an equation, you're probably going to have to convert it to seconds, no matter how long a time period it is. Temperature is a curious case because if I ask you the metric unit for temperature, you'd say, well, Celsius, and you'd be right. Actually, that is the metric unit for temperature. But the problem is that when dealing with temperatures in chemistry and physics, we need an absolute measurement of thermal energy. Absolute means that, well, temperature is a measurement of thermal energy present in an object or a sample. And, thermal energy being the kind of energy that causes the molecules to vibrate. And when we say we need an absolute scale, we need a scale where 0 really means nothing. All of these other measurement units are absolute. And in fact, all of the other measurement units in the English and metric systems, they're all absolute. A length of 0 meters is really no length at all. And it's the same as 0 inches or 0 feet. It means nothing. A mass of 0 kilograms means no mass at all, just like 0 pounds means no mass at all. 0 seconds means no time at all, just like 0 minutes and 0 hours. They all mean nothing. But in temperature, it's not like that. 0 degrees Celsius does not mean no thermal energy whatsoever. At 0 degrees Celsius, the molecules in something will still be moving somewhat. They'll be moving fairly slowly probably, but they'll still be moving. Even 0 degrees Fahrenheit, which is even colder, the items will still have some thermal energy. So what we need is a temperature scale which has, that means where the 0 point is no thermal energy whatsoever, meaning that at 0 on this temperature scale, all of that vibrational movement on the part of individual molecules has to stop. And that is called an absolute temperature scale. The absolute temperature scale based on the metric system uses units that are known as kelvins, Kelvins. Symbol is capital K, and technically it's not degrees Kelvin, although I'll let it slide if you say degrees Kelvin. And what that means is 0 degrees Kelvin is absolute zero. Absolute zero being the point at which all motion stops, including molecular or atomic vibrations. It is the lowest temperature that is even theoretically possible. So in the Kelvin system, you will have no negative temperatures ever. That's something that's useful to keep in mind, because if you're doing any kind of calculation to try to determine a temperature in kelvins and you come up with a negative number, something's wrong. Definitely. No such thing as a negative temperature in Kelvin. As I said, absolute zero is the lowest temperature that can ever be attained, even theoretically. It never actually has been attained because of the fact that all motion would have to cease. The vibration of atoms would have to stop. The motion of electrons in the atoms would have to stop. And all of the atoms would have to be lined up right next to each other in perfect order with nothing out of place, no irregularities. And that's really, really difficult to achieve. Probably in practice, not possible. So nobody has ever actually gotten to absolute zero or 0 Kelvin, not even in the laboratory, not even at the depths of outer space, billions and billions of miles from the nearest star, will you find absolute zero. In the laboratory, under the right circumstances, they've managed to come within, I think, a few thousandths of a degree of absolute zero. But the closer you get, the harder it gets to get closer. And that's probably a good sign that the calculation for absolute zero was correct. Anyway, to get a temperature in Kelvin, that is T with a little K after it, just means temperature in Kelvin, you take the temperature in degrees Celsius and add 273 degrees to it. Or in other words, temperature in Celsius is temperature in Kelvin minus 273. And so absolute zero is the same as negative 273 degrees Celsius. And that probably sounds pretty cold, although you may not quite appreciate exactly how cold, since most Americans are not that familiar with the Celsius temperature scale. In Fahrenheit, absolute zero would be negative 460. That gives you an idea of how cold it is, minus 460 Fahrenheit. And there is an absolute temperature scale that's based on Fahrenheit called the Rankine temperature scale, but we're not going to do anything with that because it's based on Fahrenheit and Fahrenheit's stupid. So not to put too fine a point on it. Okay, so we've got the standard units used for, various types of measurements in the SI system. And now we need to mention the metric prefixes. In the metric system, one other thing that's nice is not only, well, it's nice that everything is based on factors of 10, and you can change the magnitude of a unit by adding or changing a prefix in front of the unit, as opposed to English, where there's an entirely different word. If you're measuring something in inches, but it's a large object and you want to use a larger unit, you have to switch to feet. That's a different unit. It's related by a factor of 12, not 10, so you can't just move the decimal point. And it's a totally different word also. In the metric system, if you're measuring something in centimeters and it's a large object, so you'd rather use meters, Well, all you'd have to do in that case is just remove the prefix centi and you have meters. And there are 100 centimeters in a meter. So it would actually end up being the same number in meters as it is in centimeters, except you'd move the decimal point 2 places. So you wouldn't even have to do any math on that. And so we use metric prefixes to alter the magnitude of a unit. And the reason that we would want to do that is generally just to get a convenient number to deal with. If I'm measuring the length of a table, like a dining room table, then I might want to do that in, say, centimeters or maybe meters, but I'm definitely not going to want to do it in millimeters, because when in millimeters, you're going to end up with a huge number for a fairly moderate distance. And so we basically choose whatever unit gives us a convenient number to deal with. We try to choose a unit that's somewhat on the scale of what we're measuring. And then if we need to use that measurement in an equation, we might have to convert it into one of these units here. And we'll see how to do unit conversions a little bit later. Anyway, before I actually get to the prefixes, I noticed that we're out of time for the second segment of the video. So I will cut it off here and we'll pick up with the prefixes when we come back for part C.